Right, so today we will be talking about clustering, and more specifically anomaly detection with clustering. Now, first thing, can anybody tell me what that is? Okay. Can anybody tell me how many types of animals there are, roughly? Roughly 2. Okay. How do you know it's 2? Do you know what the species are? What type of shark? It doesn't matter, right? There's broadly 2 types. How do you know there are 2 types? Okay. Okay. So just by looking at certain features, we as humans can very easily interpret that there are roughly 2 types of things in that picture. Okay? And humans are very good at recognizing patterns. They see something and they can recognize stuff. They don't necessarily need to be taught. They don't need to know the details of what those things are, but they can see differences between different groups of things. What about this? Can you find Wally? I don't know, I haven't actually. Right, so why is it easy to see things here and hard to find Wally over there? There's a lot more noise that you have to process through before you get to where you want to go. Okay. And we'll get back to this slightly later on. But first, the reason for this talk, I guess, or rather the reason for the project that led to this talk, was that I was working for a financial client, and they do things like consumer FX and FX trading, but their consumer FX side was getting hit by a lot of fraud orders. And the fraud they were getting hit by was not something that some credit checks would fix, because they were using stolen identities, which means all credit checks passed. And then we have to somehow figure out which orders could potentially be fraudulent. At that time, what they were doing was their fraud department was running SQL queries against various databases, trying to troll through logs to hopefully identify what the fraud was, and they weren't getting much success. They were getting lots of false positives, a lot of fraud orders were actually going through, and the company was losing out. So the head of development basically called me over and said, OK, we have this, we don't know how to stop this, go do some research, figure out what to do. And I looked into anomaly detection, or how you catch fraud, and clustering tends to be one of the main ways at how these things are detected. There are other approaches, but clustering is very common. We'll look at what clustering is, but in essence, it's an unsupervised learning platform, or learning approach, which means that you don't have any training data. So your data, you don't have data that kind of helps you teach a system that this is a fraud order and this is not a fraud order. It's unlabelled data. It basically says that these are all the data that we have. Go and trying to figure out something. Okay. And this type of information can be used for detecting weird things or anomalies. So if you have lots and lots of real orders, some fraud orders might be considered anomalies. It's not necessarily a negative thing. So for example, if you have lots of orders in an online store, you might have certain types of customers who place very high-value orders, maybe around Black Friday. Is Black Friday a thing here? OK, cool. So you may be able to pinpoint high-value customers better using these approaches without actually necessarily knowing beforehand which ones are attractive or not. OK, that is a Theresa May moment right there. I'll leave that. OK, so clustering, the key idea is that you plot the data onto charts, and they kind of get grouped together based on their similarities or distances from each other. We'll talk about distances. And they get put into groups. So for example, over there, you have horsepower, mpg, or miles per gallon, and displacement on 3 different axes, and you can see that there are roughly 4 types of engines, I'd say. And that's all clustering is. So you're trying to find groups of things. You don't necessarily know what yellow stands for, what pink stands for, what green stands for, what blue stands for. But the fact that they are separate from each other and exhibit different behavior based on their key attributes. You're trying to find these clusters. You don't know what a cluster represents. You may not know that this cluster is fraud orders or this cluster is non-fraud orders. But after you've done the clustering, it could be that all the fraud orders are grouped together and all the non-fraud orders are separate. So that's how clustering can be used for anomaly detection. The key idea is you want clusters from your data. And the reason this is useful is because, well, birds of a feather flock together. So quite often, people who commit similar types of fraud will do it in similar ways, which will show up in their data, which may not be apparent at first, but once you run it through computers, it can be, well, quite obvious. Just like in our Wally case, or finding Wally was difficult because we have lots of data, in clustering, doing it in lower dimensions, maybe 2 axes, 3 axes, that could be quite possible just doing it in the human eye. You can just kind of look at this and say, hey, there's 4 clusters there. On 2 axes, this would be even easier. You'd see distinct groups. But as your dimensions increase, you have 10 dimensions. Or even, I mean, forget 10, even if you have 4 dimensions. That's very difficult to visualize, well, with your eyes. And as that increases to 10, 20, 50, or in case of deep learning, 100, 200, it's not something that you can reason about in your head. You're kind of reliant on computers to do that. And that is something we'll talk about, how you do. So the most simple naive clustering approaches are referred to as hierarchical clustering, and there's 2 types, agglomerative and divisive. The idea is that you start with every single point being its own cluster, and for each cluster, you compare it to every other cluster and merge the 2 clusters that are closest to each other. And you keep doing this repeatedly until you don't find clusters that are close enough to each other, or you have found the required number of clusters you set out to find. Okay. So in agglomerative hierarchical clustering, what we do is we gradually just merge clusters until we have enough clusters and things are far apart. Or in divisive hierarchical clustering, we start off with 2 clusters and keep merging them together and internally and whatnot. This thing is very easy to implement. But the problem is that it's a order of n³ operation for a naive implementation, or a n² log n operation for an optimal implementation. And you can't get better than this, because each cluster has to be compared with every single other cluster. And you can imagine if you have a lot of data and a lot of dimensions, this will be computationally very, very expensive. So that's where our other approaches come in. Right. Oh, I forgot to ask. How many of you here are data scientists? OK. And data engineers? Programmers? Everybody else. OK, cool. This talk is perfect for you guys. OK, so that brings us to k-means clustering. Have you guys heard of k-means clustering? It's the most common way of well, implementing clustering. But the idea is that you set out choosing a value of k, i.e. the number of clusters you're going to have. And then from your data, you pick k points that are sufficiently far apart. Again, we'll get to what far apart means. And then for each remaining point, you put it in the cluster that's closest, and then you shift the center of that cluster to be kind of the average of all the other points. Okay. What that looks like is that, let's say we start off with A, B, C, D, E, and we start off with 2 cluster centers. We move the center off to the nearest ones. So after the first couple of iterations, what we have is this center and this center. Is the cursor showing? Yeah. And then gradually we see that we have 2 clusters of data. Okay. And That's not difficult to implement. A lot of platforms or machine learning libraries do that for you. There's currently a k-means implementation in Spark, which there wasn't when we were looking into this a few years ago. That does a fairly good job. There's also a streaming k-means implementation, which is also quite useful. But then there are certain things that we saw when we were trying to implement k-means that was challenging for our data. So the first thing was that the cluster initializations. So we mentioned that they had to be as far away as possible from each other. So you could go through your data and try to figure out which ones are further apart and pick one of them. Or the other option is to basically, you sample your data, maybe 5%, 10% of your data, run some sort of hierarchical clustering on it, and then you pick the points that happen to be closest to the centroids, and you take it from there. Initialization isn't necessarily a big issue, but one of the other problems is picking the right value of k. And this is something that has to be done with k-means. So the idea is that you start off with k values of 2, 4, 8, 16 powers of 2, and you measure your performance, as in how cohesive each cluster is based on some distance measure, again, which we'll get to, against the number of clusters that you're having. And you'll see as you increase the number of clusters, the cohesiveness of things increase, but you reach a point where you don't get good return for the additional compute you're doing. So the idea is that you plot this, and you find a kind of knee or elbow in your curve, and that tends to be the point where you pick k, and you choose that value as what you use going forward. But another problem that we faced was that all of this was very good, and it worked really well for our samples and demos and proof of concepts, because we were kind of cheating ourselves. We picked features that were numbers and that measured against each other, so values of orders, number of times they placed orders, et cetera, et cetera. But during POC stages, we kind of skipped over the hard parts, like what do you do with categorical variables, or postcodes, or telephone numbers, or that sort of thing. So when we wanted to actually roll this out, we had to figure out some other distance measures. And there are many types of distance measures for different types of data. The first one could be a Jacquard similarity. Anybody familiar with Jacquard similarity? OK. The idea is that if you have sets of things, you take it's a ratio of intersection between two things and the union between two things. OK. So how similar they are versus the total range that they cover. And this can be done for a lot of things, like, for example, even for words. You can break down words as 2-letter pairs, 3-letter pairs, which is quite often referred to as shingles. And you can even take a distance measure based on which pairs certain sentences have or certain documents have, and find the Jacquard similarity of two entire documents. And that kind of gives you an idea of how similar these are or how different they are. Another thing could be, and this is quite useful for categorical variables, is that you take a categorical variable, let's say it has 5 different categories, you convert that into 5 Boolean Boolean features. So one feature that had 5 levels, instead of that, you have 5 Booleans that have 2 levels, 0 or 1. And the reason for doing that is that a lot of data you won't necessarily be able to order. So if you represented, I don't know, days of the week as 1, 2, 3, 4, 5, 6, 7, the problem is suddenly Friday is greater than Thursday, which makes no sense. Is Friday greater than Thursday? OK, Fridays, I mean, you have Friday beers or stuff. But from a data point of view, they're completely separate things. There's no comparison between these things. So for that, you convert the one thing that could have 7 values into 7 different features or 7 dimensions that contain 0 or 1 values. And when you do that, you effectively have a vector of 7 dimensions for that one feature, which you can find the cosine similarity by basically taking a dot product. And that represents the angle between how these vectors diverge And that can be used as a distance measure as well. Another common thing to do for comparing words is finding the edit distance. How many edits do you need to go from one word to another word? And that can serve as a measure of how similar those two words are. I mean, these things might sound silly to, see how many letters. I don't know, to go from dog to Doug, you change one vowel. What does that mean? But in the context of larger documents, they can sometimes be quite useful. There are other measures as well that you can use for measuring distances for things that are non-Euclidean. But the idea is that if you want to use these clustering algorithms, you need to figure out these distances. Another thing we mentioned for k-means was that once you've allotted points to a cluster, you need to shift the cluster centers so that it is towards what's it called? It's closer to the average. Now, you can do that for numerical things fairly easily, but for categorical things, that may not necessarily be obvious. I mean, if you are representing days from 1 to 7 with 7 different vectors, how do you find an average of that? Is the average of Saturday and Tuesday Monday? Or it makes no sense. So in that case, you basically measure the distances, and you find the value that minimizes the distance, and you pick that particular value. Okay, so some problems that we found with k-means are that the clusters, because they're based on distance measures or absolute distances, they tend to be perfect spheres. It's the distance between one point, the cluster center or centroid, and distance becomes a radius of a sphere. And that's the sphere of influence for that particular cluster. You cannot have non-uniform spheres when you're dealing with k-means. Okay. And the other problem is that to be able to run this calculation, you need to hold all the data in memory for quick computation. And doing that on one machine works for POCs and sample data. When you have 500 gigs, that doesn't work very well. Okay? That's about it for k-means. Any questions so far? Nope. OK. So that kind of takes us to BFR, or the Bradley, Fayyad, and Reina algorithm, which is an implementation approach towards k-means that can work for larger data sets. You don't need to hold all the data points in memory. You just need to hold some summaries. Okay. You still need to hold the summaries in memory, so it's difficult to do a parallel computation for this, but it does help with storage. It also helps where your data is not necessarily the clusters aren't pure spheres. They can be ovoids or egg-shaped. We'll get to how that happens a bit later. But the idea here is that you have 3 sets that you use. The first is called a discard set. The second is represented by this thing. The second types of sets are called, or rather, the second set is called a compressed set. And the third set are called retained set. Okay. What the discard set and the compressed set do is that they hold summaries of cluster information. And the information they hold is the number of points in that cluster or mini-cluster, in the case of compressed sets, the number of points, the sum of the values for all of the data points, and the sum of the squares. Now, can anyone guess why we're storing these 3 values as summaries? Anybody? Nope. OK, so these 3 values are quite often used for streaming algorithms as well. The idea is that if you store the number, the sum of values, and the sum of squares, then at any point in time, you can get the mean by dividing the sum by n, and you can get the standard deviation by taking the sum of squares, dividing n, square root. OK, so the statistical summaries for anything can be computed while you're adding new points. whenever you get a data point, what you're doing is you're updating n, so n becomes n plus 1. You're increasing the sum, and you're increasing the sum of squares. So it's like a running count of values, and with these 3 values, at any point you can get the total number of items there, the mean, and the standard deviation. And those things can be quite useful for certain calculations that we'll get to in one moment. OK, so the way BFR works is that, again, you start with k-points. And the way you start with k-points can be similar to how you do it for k-means, as in you can initialize, well, you can take a sample, get an initial value of k. Unlike k-means, you don't necessarily have to end up with k clusters just because you started with k-points. You can have more than k by the end of your data processing without actually having to go k plus 1, k plus 2 again. Okay. So we start off with roughly k-points, or k-points. And then we can read in data in chunks. And this is actually quite key for processing large amounts of data. You might have large amounts of data in, I don't know, Parquet files, Cassandra partitions, or whatever. But the idea is that you read in entire chunks at a time. You don't necessarily have to do it one by one. Okay. With a few tweaks, this can be done in parallel as well. There's a separate algorithm for doing that. But the idea is that you read it in chunks. And then for each chunk, any data point that is close enough to a clusteroid, or cluster center, you put it into that cluster. And what we mean by putting it into a cluster means that we simply update n, we update the sum for n, and we update the sum of squares for the n. So it's still those 3 variables that we have, but then we don't actually have to retain all the data and all the dimensions for each and every data point. We're just updating the summary and then discarding the data point. That's why it's called the discard set. We still keep the summaries. The summaries are very important, but we don't need to hold on to data for every single data point. That's where we save a ton of memory. OK, so if it's close to a centroid, we just put it in. If it's not close enough to a centroid, then we cluster them in main memory. And that clustering can use hierarchical clustering, k-means, or whatever, but that's running entirely in memory on small amounts of data for that particular chunk. So we kept adding them in, and then we've got a secondary clustering, if you will, in memory that's happening. And that is how we get the mini clusters. And once we are done processing the chunks, whatever is in mini clusters, we have them as our compressed set. So we have our cluster centers, and we have a lot of mini clusters. What's it called? These bits represent our clusters. And the in-memory clustering we've done that we couldn't put into we couldn't assign to a centroid becomes our mini clusters, and they are represented by the compressed sets. Okay. And whatever, after running clustering in memory for the things that could not be put into clusters, and they are effectively singletons, we retain all the information about them in the retained set. So we haven't held on to data points, or rather all of the data points, for the things that belong to clusters. So the discard set, we haven't held on to any information about anything that is in the compressed set. We've only held on to all of the information for the things that are in the retained set. OK. Ooh, went too far. OK, and then once we have we've processed these things, and we have our mini clusters, we then see if any of those mini clusters can themselves be merged into slightly larger ones. And that will convert some mini clusters into bigger mini clusters. At that point, they will probably not go into a centroid, but they will exist as slightly larger compressed sets. So at the end of this, we have, once we've done all the chunks, we have our cluster centers, we have our mini clusters, and then we have our retained set, which consists of points that don't belong to any mini clusters or bigger clusters. All right. For the last chunk, we need to decide what we do with the retained set points. Okay. If the point is close enough to a cluster, and it depends on our definition of what close enough is, which we'll get to, then we can just assign it as part of a cluster. Otherwise, we can treat that as a true anomaly, I don't know, error in data or something, and we can completely discard it. One other option is to treat it as yet another category and just leave it as a cluster on its own. Okay. Now, I mentioned the notion of distance from a centroid and distance from a cluster. So for k-means, or basic k-means, the distance from a cluster was basically whatever distance measure we had, like the Euclidean distance or the edit distance or whatever. For BFR, and that led to spherical clusters. For BFR, we have the notion of Mahalanobis distance. Okay, quite a mouthful. But the idea for the Mahalanobis distance is actually quite simple. It's basically saying that how many standard deviations of a cluster away from the cluster is a data point. So how far away is it? But instead of a distance being the answer to how far away is it, it's how many standard deviations of that cluster is it far away from. So if you have a very tight-knit cluster, the standard deviation is going to be fairly close, right? So if a point is out there, it might be 4 or 5 standard deviations away. If something is over 3 standard deviations away from the cluster, then it's highly unlikely that that thing belongs there. Okay. So if you have a cluster, let's say, over here, and your data point is over here, and this is a tight-knit cluster, it's very unlikely that this belongs to here. But then if you have a cluster that's over here, right, that's fairly widespread, the standard deviation for this, it turns out that this point, even though it's further away from this cluster, it's further away, but in terms of standard deviations, this has a much larger standard deviation. So this point could fall into 1, 2 standard deviations of this larger cluster. So in that case, you would assign this to that one. Or you could choose to not assign it to anybody. It's saying it's more than 3 standard deviations away from any cluster, so it doesn't belong to any of them. Okay. And what this allows us to do is that it's as long as our axes or dimensions are completely independent, there's no reason for clusters to be limited to purely spherical values. Because of the standard deviation approach that we're doing in terms of measures, they can be kind of egg-shaped. So in 2 dimensions, it's egg-shaped. But the idea is that the standard deviation need not be exactly the same, or you don't need to normalize all your data points to be exactly the same for all dimensions. They just care about standard deviation along each axis independently. Now, if different axes were to interact with each other, where instead of, say, along the x-axis and y-axis, if there's some interaction terms where it's kind of off to at an angle, then this will not work. Okay, the axes have to be completely independent for BFR to work. Now, what this gives us is that we need less main memory. We don't need to hold all of the data points when running our clustering. We just need to store the n sum and sum of squares. And it gives us slightly irregular cluster configurations. Okay. Any questions on BFR? Okay. So we did all this, and initial results were quite good. But then what we found was that some of our clusters, they don't necessarily follow spherical shapes or elliptical shapes for some of our dimensions. They're quite irregular. And if they are irregular shapes, like, say, the one over there, then k-means has no chance of, or BFR has no chance of effectively finding these clusters. And that's where the CURE algorithm comes in. So CURE stands for clustering using representatives. And it allows for irregular clusters and shapes, or cluster shapes. So the way CURE works is that you sample the data, you cluster it in main memory using any standardized thing. dbScan happens to be quite common. dbScan is where if you find clusters where 2 points are close together, you merge them. And you keep on merging until no clusters have points that are close to each other. So you cluster them in main memory, and then you take representative points from each cluster. Once you've got the representatives, we'll look at an example in a moment, then you shrink it towards the center. And then you merge any clusters that happen to be close together. Once you've done that, you then go through your remaining data points, and you assign them to whichever cluster is closest. So what does that look like? So here we have data, that simplified data that's plotted on 2 dimensions. And if we plot it on 2 dimensions, you can see there's a cluster here that is completely surrounded by another cluster there. OK. Now, you can imagine how this is very difficult for k-means to identify. Because, well, any notion of distance from a center would be effectively the same, because the center of this cluster is exactly the same as the center of the outer cluster. OK. And so what we do is we take this, we cluster it in main memory, let's say with dbscan. We shrink it. So you can see that we started off with this. We shrink it towards the center. And then effectively we have one cluster of data points there and one cluster of data points there. Right? These kind of come out of the ring slightly closer to the center. When we have this, and then, oh, sorry. I slipped a slide. Right. Sorry. Right. So what happens is that after we have this, we just go through each of our remaining data points and assign them to whichever cluster is closest. So we could assign them to here, or we could assign them to there. The notion of closeness can be distance from the center, which would not work for this type of thing. It could be the distance from any of the points in the cluster, which would work quite well. So if it's quite close to here, it would belong to this cluster. If it's quite close to here, it would belong to the outer cluster. It could also be the average distance from any of the data points in the cluster. It could be the minimum distance to any of the data points of the cluster. It could be the total distance from all of the data points from that cluster, so on and so forth. It really depends on what your data looks like and well, how it behaves with different approaches. So trial and error, unfortunately. Right. So there are other techniques as well. Yep. Yep. Yeah. So the idea is that you use some sort of main memory clustering algorithm first, for which you'd use dbscan or something. So for this, if you use k-means in memory, that's not going to work, obviously. OK. But then what you do is use some sort of main memory clustering on the sample. And then from those clusters, you take representative data points. So you don't take all of them. You take a few of them. And the reason for that is saving on computation. That's all it is. OK. And once you have that, you move it slightly closer to the center. And the problem with that is that for that to work, you again have to kind of have a Euclidean distance. You can't move categories towards the center. That doesn't make sense, right? So the limitation of this is that it only works for numeric values, not for categories. So the reason for shifting it towards the center, as in this case, is basically so that when you are assigning newer points, the chances of it going to the wrong cluster are effectively minimized in that case. Okay, so this sort of clustering then works for things like concentric circles. If you have things where you have like S-shaped data, these types of things work very well for that. Okay, does that help? Okay, cool. Right. So I mentioned dbscan. You'd probably use something like dbscan as the first phase of CURE anyway. I won't go into the details of dbscan, but effectively it just merges clusters as you go along. So it's very easy to do as a kind of streaming type of thing. grgpf is something that is very similar to, I think, how we did BFR. But it can be done distributed and parallel. Unfortunately, libraries like, say, Spark and mllib, or Spark's mllib, they do k-means. They do k-means fairly well, But then if you have things like non-spherical clusters, it's not really going to be useful. And the standard libraries don't necessarily have all the implementations. So you will find yourself implementing these in code, even on large amounts of data, by yourself, because I don't know whether there are standardized big data implementations for this. Or I haven't found any yet. Okay. So GRGPF is basically that type of approach where you keep ends, sum of squares, and work on large amounts of data on lots of machines at the same time. So it's a slight tweak. BDMO is an algorithm that can work for streaming clusters. So basically, if you have timed windows of things where your clusters are moving throughout a time series and are in effect for a limited amount of time, and you have streaming data coming in, and in real time you're trying to guess which type of grouping it belongs to, then BDMO is a clustering thing to look at. In our case, BDMO wasn't necessary, and once we'd implemented GRGPF, we actually got what we needed, really. And so we implemented all of this, and then we analyzed data, and it basically turned out that the majority of the fraud stuff we were getting was people using certain groups of telephone numbers. They were somehow sharing telephone numbers across different postcodes. And so if you got the same telephone number calling from many different postcodes, then that turned out to be the main identifier of fraud. So we spent like a few weeks doing all this cool stuff. Had we not done all this cool stuff, then we wouldn't have actually got it. But in the end, it turned out that we could just run that simple SQL query, and that triggered just with a success rate of over like 90%, and they were happy with that. So yeah, cool. Anyhow, that's it. Any questions? OK, so most of the examples here are from a book called Mining of Massive Datasets, or MMDS. It's a free PDF online. It deals with a lot of, let's see if I can find that. There you go. So it's basically Jeff Ullman's book, along with Yuri Laskovich and Anand Rajamaran. There was an online course for it, which was actually really difficult and really good. But the idea is that it goes through many common things in data analysis and statistics, but then applies it for big amounts of data, things that you can't just fire up RStudio or Excel and just analyze because there's so much data. So things that need distributed processing or things that need stream processing. It goes obviously beyond clustering. There's things like recommendation engines. There's things like streaming computations, social media analysis, that sort of stuff. But it's quite practical techniques and things that you won't necessarily find implemented out of the box in MLlib or any of the popular libraries. Most of those, the problems that it covers, you will find solutions for them for things like scikit-learn. But again, the problem being that they'll only work on single machines, not for large amounts of data. So it's a really good book, and I highly recommend it. But that's it. Thanks for coming.